So, good morning, everyone. I'm Robert Boyd, and I was going to say University of Ottawa, which is true, but I'm lucky that I'm lucky that I have 3 jobs and only 1 paycheck. So I also have affiliations with the University of Glasgow and the University of Rochester, although it was at Rochester, of course, where I wrote the Nonlinear Optics book. But once I get later on into my lectures where I'm talking about some of the research, the other 2 affiliations will become very important. So, okay, so why study nonlinear optics? Well, we can each have our own view of this, but to me, it's that it's good fundamental physics. It also leads to important applications, and it's a lot of fun. And all 3 of these are very important to me because I am, first of all, a physicist. I'm, second of all, an engineer. Being a physicist, I think, does not preclude one from doing things that are useful. And nonlinear optics and photonics are disciplines in which the fundamental aspects and the engineering aspects just mesh together so well. And I think for that reason, that's one of the reasons why I love nonlinear optics so much. Also, when I teach the full course on nonlinear optics, I usually start off by saying that this is not a course in nonlinear optics. It's actually a course in optical physics seen through the eyes of somebody who works in nonlinear optics. Nonlinear optics, the formalism of nonlinear optics, it can be very useful for categorizing a very broad range of physics. Oh, and it's a lot of fun. Well, if it weren't fun, why would we work as hard as we do? Okay, so those are the brief introductory comments. Oh, and just a brief memorial in case people did not hear the news. Charlestown's pioneer of nonlinear optics and arguably the inventor of the field of photonics. Let me read his first patent. Arguably the inventor of the field of photonics passed away just earlier this year. He, of course, was the inventor of the maser and the laser, won the Nobel Prize in 1964. He was the advisor to 3 US presidents, and at a very personal level, he was my teacher, my mentor, and my friend. And if you want to read more about his life and his contributions, there's an obituary in Nature that you might want to take a look at. Okay, so let's move into the basic material. So first of all, let's talk about what is nonlinear optics and what are the methods that we would use to describe nonlinear optics. And there are moments in life that you wish that the room were darker. And this is one of them. You would not believe how beautiful this picture is, and you wouldn't believe how hard my students and I worked to take this picture. But this is a picture, a laboratory demo of what's called light-by-light scattering. And from a fundamental point of view, this is the Dobruch diagram that describes light-by-light scattering. And you see that 2 photons enter here, they interact with one another, and they leave here. And conserve energy and momentum and all that. It's been predicted that the nonlinearity of the electromagnetic vacuum can lead to light-by-light scattering, but that's never been observed. Gerard Mourou is working very hard at trying to observe this process, so it's very regrettable that he got sick, got ill, and could not be with us last night. This has never been observed, but laser intensities seem to be within reach where one could see light-by-light scattering in the vacuum. In our work, we developed this very, very highly nonlinear optical medium. It's a dye molecule doped into a boric acid glass. And you see that 2 laser beams enter here. They interfere with one another inside the medium. This creates a sinusoidal modulation of the refractive index. Each beam scatters off of that modulation, and 2 beams entered, but 4 beams left. So there in front of your eyes is light-by-light scattering. It's my it's my non-photonics friends who find this remarkable. I mean, it conjures up pictures from Star Wars, where one lightsaber interacts with another lightsaber. This also gives you an intuitive picture of the connection between nonlinear optics and photonics, because if you think of this, if you think about it, this is what you would call an AND gate. Imagine putting a detector here or here. Now, you will get light there only if both of these input beams are on. If both these input beams are on, you get an output at one of these side modes. If either of them or both of them are off, then you do not get it. Of course, this is not the engineering version of an AND gate, but I think it establishes in a very illustrative way the connection between nonlinear optics and the field of photonics. Okay, so what do we mean by nonlinear optics? Well, this is what I mean, because I've spent a good fraction of my professional life working on nonlinear optics from a pedagogical point of view. Even with the extended amount of time that I've been given to lecture today, we cannot go through the entire book. So, but let me do this. Let me summarize the book in one page. And then if you fall asleep, it doesn't matter, because I've summarized the entire book for you. Okay, this is a simple formulation of the theory of nonlinear optics. And in this very simple formulation, we take the polarization, which is the induced dipole moment per unit volume, and we express it as a power series in the electric field amplitude E. And, well, at one level, these are just coefficients in a power series expansion. But it turns out that each of these really has a very strong intuitive meaning. Chi1 describes linear optics. Chi2 describes second-order effects, such as second harmonic generation. Chi3 describes any third-order effect, such as third harmonic generation, sort of an obvious generalization of second harmonic generation. But in fact, any type of four-wave mixing process, here, 3 beams enter, 1 beam leave, any of these can be described as a Chi3 nonlinearity. And even more generally, any time that the refractive index shows a linear dependence upon the intensity, this is also described by Chi3. This coefficient N2, which is very useful in the laboratory, and this coefficient Chi3, which is very useful when doing fundamental studies of nonlinear optics, are related to one another in just this simple manner. Now, I said simple formulation of the theory of nonlinear optics. So, what would be left out, or what would you want to put in to have a more complete theory? Well, first of all, Chi1, Chi2, and Chi3 are tensors, not scalar quantities. And this point will be exploited by several lectures as the week goes on, so many that I've forgotten exactly who all is talking about the tensor nature of the nonlinear response. The other thing that's left out here is that, well, as written, we're implicitly assuming that this is in the time domain. But in fact, if you want to describe this more generally, you have to take into account that each of these coefficients is itself frequency dependent. So then you have to transform into the frequency domain. And this is something that I'm sure will come up as the 2 weeks progress, because it's only when you're doing the simplest theory of nonlinear optics that you can proceed in this manner. Okay, so let's just as an introduction, just go through some of these standard nonlinear optical processes, and let's take a look at how they work. And sort of the most obvious one, and in fact the first of the nonlinear optical processes that was discovered after the invention of the laser is a second harmonic generation. Here a beam of light at frequency omega enters a material with a second order nonlinear optical response, and some fraction, often some small fraction of the light gets converted from frequency omega to frequency 2 omega. It is very useful, surprisingly useful, how much intuition can be developed by understanding these processes in terms of an energy level diagram. We would think of this as a single quantum mechanical process in which two photons are simultaneously extracted from the input laser beam, and a single photon is created at the sum frequency. And, well, a number of years back, graduate student, postdoc, and myself were asked to write a review article for one of these encyclopedias on nonlinear science. So we took this photograph for them, showing you that it really does work. So here's a laser beam entering a crystal. Then you have a prism. The prism separates the fundamental at 800 nanometers from the second harmonic light at 400 nanometers. Okay, so this is second harmonic generation. Now, you say, what are some other Chi2 processes? Well, an almost obvious generalization is sum frequency generation. Here, the two input frequencies can be different, but other than that, the basic intuition is the same. A photon at frequency omega 1 and a photon at frequency omega 2 are simultaneously annihilated, and a single photon at frequency omega 3 is created. Now, let's go back for a second. Why do people care about second harmonic generation? Well, if you want a green laser pointer, you need to make use of second harmonic generation. The world still does not have a good way of making laser diodes that work in the green. So it's much more efficient to build a laser that's based on the neodymium ion, so neodymium YILF, as it turns out. So so this is actually what's going on inside of a laser pointer. Great beginning graduate student demonstration. Laboratory project. Project part 1, take apart a laser pointer and see how it works. Project part 2, put it back together and see if you can still make it work. Many of my students get past stage 1. Okay, so the green laser pointer, and I would just say, it just makes you feel so good to walk around life always having a nonlinear optical device either in your pocket or in your briefcase. Okay, so why would the world care about sum frequency generation? Well, one is just to get tunable light. Let's say that one of these is just a very intense laser beam, and the other is a beam of light from a tunable laser, perhaps a Ti-sapphire laser. Well, you can take the tunability and then extend it to the ultraviolet just by mixing it with another visible laser beam. Second application is something that's called infrared upconversion. Maybe one of these is an infrared frequency and the other is a visible frequency. In this case, the sum frequency will be in the visible, but at a slightly shorter wavelength. Now, it turns out the technology is such that we still do not have good single photon detectors in the infrared, but we have great single photon detectors in the visible. So while a bit indirect, this has been demonstrated to be a very efficient way to build single photon detectors that work in the infrared. Okay, now, difference frequency generation. Your first thought is that, well, this is another simple generalization of sum frequency generation, but in fact there's a real twist that comes in here. So here, let's assume that we have two frequencies, omega 1 and omega 2. Let's say that omega 1 is larger than omega 2, and we are trying to generate light at omega 3, which is omega 1 minus omega 2. Now, the only way you can draw one of these energy level diagrams is with omega 1 going up and omega 2 going down, generating omega 3. So this immediately tells you, well, if you believe the diagram. This or if you believe in energy conservation, this immediately tells you that in order to generate a photon at frequency omega 3, you have to amplify the signal that was present at omega 2. So in fact, you can build a device called an optical parametric oscillator based on this principle. See, since there is gain at frequency omega 2, you can take your nonlinear crystal, place it inside of an optical resonator, just like a laser cavity, except now you have a nonlinear element inside rather than a gain element inside. So you pump this and with frequency omega 1. We'll get to phase matching in a few minutes, but by changing the orientation of the crystal, you can determine which combination of omega 2 and omega 3 will be generated. When this was discovered in the 1960s, the first thought is, this is incredible. Second thought is that, but the second thing that happened is that the dye laser got invented. And at that time, it was considered that the dye laser was a far more effective way of producing tunable radiation. So the optical parametric oscillator sort of fell out of favor for many, many years, and then came back into favor as a result of work of many people. The prime example being Majid Ebrahimzadeh, who's speaking at this school. So I'll let him tell you the story of this. But why do people prefer optical parametric oscillators to dye lasers? Well, dye lasers are tunable, but they're tunable over maybe 50 to 100 nanometers, whereas an optical parametric oscillator can tune all the way from the ultraviolet into the infrared. So you don't have to change these nasty chemical dyes every time you want to change wavelength. You just, now you go to the computer keyboard, you say, give me light at 567.34 nanometers, and the crystal turns, the cavity adjusts, and you get that output anywhere in the visible. Okay, so the other, another related process to difference frequency generation is what's known as parametric downconversion. Difference here is that you apply only the pump laser, here I'll call it omega p, and you generate a signal and an idler photon, both of which grow from noise. You do not put any light into the system at either of these two output frequencies. This is a purely quantum process in this case, in that the, if you want, the vacuum fluctuations are what seed this process here. Now, that's all I want to say about this now, because my third lecture in this physics school is going to be about how we use nonlinear optics to create quantum states of light. So I'm mentioning this now just to make sure we all know how parametric downconversion fits into the big picture of how nonlinear optics works. Okay, so moving on to third order processes, we have third harmonic generation, same story. 3 photons each at omega are simultaneously annihilated. Photon at frequency 3 omega is created. By the way, I draw these pictures this way, showing that the output contains both omega and 3 omega, so that we remind ourselves that these are often not efficient processes, that a small fraction of the light turns into light at 3 omega, and there's a very strong output beam at the fundamental frequency. Okay, so mentioned this already, but let's go through it in a little more detail now. Chi-3 processes also lead to the intensity dependence of the index of refraction. There are two fundamental geometries in which one could measure the intensity-dependent index of refraction. One of them is you take a single laser beam at frequency omega, pass it through this nonlinear material, and measure the phase that's acquired by the beam, and specifically extract the nonlinear contribution to the phase of the beam. We'll call that self-phase modulation. You can also do it using two beams. We call this cross-phase modulation. Here, a strong beam at frequency omega interacts with the probe beam. The probe beam, let's say it's very weak, the probe beam picks up a nonlinear phase shift as a consequence of its interaction with the strong pump beam. Don't want to go into all the details here, but if you go through the calculation very carefully, you find that the N2 for this effect is twice as large as the N2 for the single beam effect. And if you don't know that, I can recommend a book where the details are worked out in detail. Also, a straightforward calculation can tell you what the value of N2 is. Here I'm thinking of N2 for this case of self-phase modulation. So N2 is related to chi3, but it also depends on some other properties of the material, such as the linear refractive index, well, and epsilon 0 and C. Let me just point out, without giving away too many secrets, because I'm probably not the only person who knows the secret, there's great interest in the photonics community in studying materials they're called epsilon Nearzero materials. Often they are metamaterials, but you can design a metamaterial in such a way that the dielectric constant is nearly equal to 0. Well, you can design it so that the real part of the dielectric constant is 0. But now, what happens to N naught? If the dielectric constant is 0, N naught is going to be very, very small, and that tells you that N2 is going to be anomalously large. So we are working on this, but I think other people are working on it as well. Okay, now there's a very crucial issue involving the role of symmetry in nonlinear optics. This is a generally, it's a crucial feature of nonlinear optics. This will come up in many of the lectures that we hear over the next 2 weeks. The general statement is that if you know the point group symmetry of any material, that leads to important restrictions on the possible form of the nonlinear coefficients chi2 and chi3. And it's group theoretical, and that would take me too far afield in this lecture here. I will let the other people, no, sir, I'm only going to lecture on the easy material. I will let other lecturers teach the difficult material. But in terms of the role of material symmetry in nonlinear optics, perhaps the most compelling example is the statement given here that chi2 vanishes identically for a material possessing a center of inversion symmetry, or as we call this, a centrosymmetric material. Let's just explore this point a little bit. Let's ask, what is the potential function U that binds an electron in an atom to its equilibrium position? So, everybody's simple model of optical effects, we call it the Lorentz model of the atom. We say that the potential well is harmonic, or that the electron is bound to the atom with a force that obeys Hooke's law. So if that were rigorously true, this potential well would be a perfect parabola, and there would be perfectly no nonlinear response. But in real materials, the actual potential well deviates from a parabola. And there's two ways that this can happen. Well, first of all, in a centrosymmetric material, just because the material is centrosymmetric, the actual potential well has to be symmetric. So the potential at plus x is the same as the potential at minus x. But for a non-centrosymmetric material, it can be different on either side. So the way this was drawn, the force is stiffer for positive values of x and weaker for negative values of x. And note that I drew this with the potential getting weaker on both sides. This is consistent with the fact that you can ionize an atom. If you apply a field that's strong enough, you just pull the electron away from the atom. So in nature, potential wells tend to be of this form here. But now, let's take a careful look at the consequences of the fact that the deviation from a parabola can be either non-central symmetric or centrosymmetric. So let's take a look at, so let's assume that we apply an electric field. The field as a function of time is just a sinusoid, very simple example. For the case of a linear medium, the polarization will also just track the electric field of the input beam. But now let's assume that it's for a centrosymmetric medium. And let's be honest, I have greatly accentuated what the nature of the harmonic distortion would be. But you see that the response becomes proportionately larger at the peaks of the applied electric field. But for a non-central symmetric material, it's perhaps the potential is stiffer for positive displacements, so it doesn't go up quite as high, and it's weaker for negative displacements, so it comes down here. Now, what is the point of all of this? If you try to synthesize this waveform in terms of a power series expansion, you can do this by including only even values of n in chi n. So you can express this as a combination of no, set it backwards. Sorry. Okay, this one here you can express as a power series involving chi 1, chi 2, chi 3, chi 4, chi 5. This one down here you can represent. You need the odd orders as well. The even orders as well. You get chi 2, chi 3, chi 4, chi 5, etc. Okay, let's move on before I mess this up some more. Okay. Okay, so everything now we talked about the nature of the nonlinear susceptibility. We haven't talked about Maxwell's equations yet. So, but this is supposed to be optics, so we really need to know how light will propagate through one of these nonlinear materials. So, regrettably, let's just work out an example. And I know it's a little early in the morning to be doing mathematical derivations, but probably better in the morning than in the evening when we're all half asleep. My apologies to the evening speaker. Okay, so let's really do it. Let's work out an example. So let's say that we want to treat second harmonic generation. So let's assume, well, same situation as before, but now we're going to do it a little bit more rigorously. We apply a field amplitude E1, frequency omega, to a nonlinear material characterized by chi 2. And the question we ask is, what is the strength of the electric field that we generate at frequency 2 omega? So let's represent the input field. I'm using my personal notation. I will use a tilde for quantities that are time varying. So we can express the time and spatially varying incident field by a spatially dependent field amplitude and an exponential phase factor plus complex conjugate. we can call this a slowly varying field amplitude. No, this is the rapidly varying field amplitude. We can also represent E as A times e to the I kz, in which case we can represent it in this form here. So A1 is the slowly varying field amplitude. We factor out this exponential spatial and time dependence, and we have, of course, have to add the complex conjugate because any physically meaningful field has to be real. Now, we're trying to calculate how much field we create at frequency omega 2. Let's call that field amplitude E2, and we represent it by the same type of decomposition. But there's an important notational difference here. Let's assume that A1 is constant, that the pump field does not lose power as it propagates, consistent with the fact that we're assuming this is not a very efficient process. But the whole idea of the calculation is to ask, how does this electric field at the second harmonic, how does this evolve in time? So we will explicitly allow A2 to be a function of Z. And of course, K1 and K2 are what you would have thought. K1 is the refractive index at omega 1 times omega over c. K2 is the refractive index at twice omega times twice omega over c. Okay, so in words, we have assumed that the pump wave E1 is undepleted by the nonlinear interaction. We took A2 to be a function of Z to allow the second harmonic wave to grow with Z. And okay, now, we formulate nonlinear optics in terms of the polarization. Polarization is the dipole moment per unit volume. So we want to represent P2 as some amplitude times a time factor that oscillates at frequency 2 omega. Using some just a technical point, applying that power series expansion that I had in the first slide, you can convince yourself that this amplitude P2 is epsilon 0 times chi2 times E1 squared, but E1 is equal to this. So P2 is epsilon 0 chi2 A1 squared e to the 2ik1z. Okay, so this is just notation, but we got to do it. Okay, now where's the physics? Well, the physics is that the field that we're trying to generate at frequency twice omega has to obey the wave equation. So this is the most general form of the scalar wave equation. Again, the vector parts, tensor parts are suppressed. We've included a source term here. So if you just start with Maxwell's equations and derive the wave equation the way you've been taught since you were very young, and if you include both the E field and the D field, right? The D field has a contribution from the polarization of the material, you end up with a wave equation of this form here. Now, how do we understand this wave equation? Well, first, we've derived it. So there's no doubting its validity. But how do we understand it? So first of all, if there is no nonlinear response, the right-hand side would be equal to 0. So this is the wave equation describing the free propagation of light in a uniform material medium. And of course, this possesses all the solutions that we know and love. It possesses the infinite plane wave as one example. It possesses the spherical outgoing wave as another example. The Gaussian laser beam, well, is an approximate solution to this. You can take the limit, you can take the paraxial limit of the wave equation, and in the paraxial limit, the Gaussian laser beam is an exact solution. So anyway, this is the equation we know and love. This is the wave equation as it is best written for use in nonlinear optics. We know what the polarization is. We just have to now solve this to find the evolution of the electric field amplitude. So we do it. I said the first term here is the Laplacian of E2. So you just work this out. You substitute for E2 in terms of A2 that we defined already. We now make an approximation. This is known as the slowly varying amplitude approximation. And this approximation says that this term here is much smaller than this term here. And if you think this through, roughly speaking, this is telling you that, of course, A2 is allowed to change spatially, but that the fractional change in a distance of the order of an optical wavelength is very small. A2 is allowed to change, but it changes only on a distance scale much larger than a wavelength. And under those conditions, this term is much larger than this one. Okay, now going back to the wave equation, we also need to calculate the second time derivative of A2, and we get, well, that just pulls down 2 omega squared with a minus sign. Similarly, we do the same thing for the polarization, determine its second time derivative. We take this, this, and this, plug it back into the wave equation from the last page, and this is what we find. Combining it and then just rewriting it a little bit. Twice I times K2 dA2 dZ is equal to minus 4 omega squared over C squared chi 2 A1 squared times e to the I delta kz. So how do we understand this equation? Well, first of all, what shows up here is this quantity delta k, which is known as the phase mismatch or the wave vector mismatch. And of course, it's crucially important in determining the efficiency of nonlinear optical interactions. You sort of know that you're dealing with nonlinear optics when you find a delta k in an equation, for almost obvious reasons. And if it's not obviously obvious, crank your way through it. In linear optics, there's no way that you can get a wave vector mismatch. Right? A wave is always in phase with itself. It's only in nonlinear optics where, where the phase velocity of the fundamental can be different from the phase velocity of the wave that you're trying to create, that you have this problem, or this issue of this wave vector mismatch. We'll explore this in detail in a moment. Other thing to notice is that there's an omega squared dependence here. So the higher the frequency, well, all else being equal, and let's say that all else is equal because it often is, all else being equal, nonlinear interactions become stronger, more dominant at high frequency than at low frequency. And I think you can think of that in terms of the wavelength of light being one of the characteristic distance scales. So for a fixed length of material, as the frequency gets higher, the wavelength gets smaller, you have more wavelengths, and each wavelength of light, you get a certain contribution to the second harmonic, and they add up coherently, and you even get a square factor there. Okay, so this is the reduced form of the wave equation that applies to second harmonic generation. Okay, so now if delta k were equal to 0, this e to the I delta kz just disappears here. You get a very, very simple equation, right? Because we've assumed that A1 is a constant. So the right-hand side of this equation is just a constant. You solve this, and you find that A2, the amplitude of the generated light at the output of the crystal, is given by this form here. Usually, we care about the intensity of the generated light. The intensity is proportional to the square of A2, so we get this form here. So what are we supposed to see from this result? We see that the second harmonic intensity scales as the square of the input intensity and also as the square of the length of the crystal. Well, being nonlinear optics, it's perhaps not surprising that the output intensity scales like the square of the input intensity. Why does it scale like the length of the crystal? Well, here's one way of trying to understand this. In any material sample, you have a very large number of oscillating dipoles. The dipole might be associated with each molecular unit inside of the crystal. Each dipole itself emits in a standard dipole emission pattern, but if you have a very large number of these dipoles, and if they are all oscillating with the proper phase relationship, the field adds up coherently in the forward direction, adds up incoherently in all other directions. If there's something like an Avogadro number of molecules inside the sample, the forward emission is enhanced with respect to the backward emission by about a factor of 10 to the 23rd, which is something you don't ignore. So the light tends to be emitted in a very intense beam coming out in the forward direction. So it seems as if getting delta K equal to 0 is highly desirable. We can make that thought a bit more explicit, because if delta K is non-zero, you can still solve our equation 8, and the only difference is that now you have the same term as before, but you have a sinc squared of delta K L over 2. And here's a plot of the sinc squared function. And you see that it is strongly peaked at delta K equals 0. And if delta K is non-zero, you lose efficiency. In fact, there are certain values of delta K in which you get 0 efficiency, a complete destructive interference, say, of the light generated in the first half of the crystal with the light generated in the second half of the crystal. But the intuition then is that delta KL must be much smaller than pi radians in order for efficient second harmonic generation to occur. Okay, so how do we get delta K equal to 0? Before I go on, why do people care about second harmonic generation? Well, I've told you one reason, that's for green laser pointers. Perhaps a more significant reason is that there's a whole community of people who work in the field of biophotonics. And one thing that they do is to build nonlinear microscopes. In fact, going back through the literature, you find that the very first group that did this with femtosecond lasers was the group of Alistair Ferguson from Glasgow in Scotland. And the first author of this paper was a man named Curley. Note that it's spelled C-U-R-L-E-Y, because if you think of Curley et al. Spelled the other way, you cannot help thinking of the Three Stooges. I'm not sure that they used Latin to describe themselves as Curley et al. But the Three Stooges were Curly, Larry, and Moe. See, Curly is the one who had almost no hair. That's why that was part of the joke. Okay, so as my lectures progress this week, we will find other examples in which just changing one letter in somebody's name leads to a profound change in the implication of what you are thinking about. I still cannot read my book. Every time I read Curly at all, I sort of burst into laughter, either internally or sometimes externally, sometimes only internally. Okay, back to nonlinear optics. So how to achieve phase matching? Okay, we've said that you really want delta K equal to 0 in order for I'll use the word parametric nonlinear optical processes. How embarrassing, I didn't get this word in yet. So in parametric nonlinear optical processes, you want delta K equal to 0. And by the way delta K was defined, let's just go back. okay, delta K is twice K1 minus K2. So, so that means, well, in general, N1 omega 1 over C plus N2 omega 2 over C needs to be equal to N3 omega 3 over C, where omega 1 plus omega 2 is equal to omega 3. So you stare at that for a second and you say, are these compatible? Well, first of all, for an isotropic dispersive material, they are not. And the reason is that in a dispersive material, the refractive index tends to be an increasing function of frequency. Well, I mean, you can put a resonance in the middle of this, and then that's not true. But usually usually in nonlinear optics, we want to work in materials in which we are very, very far away from any resonance because you get lots of absorption associated with the resonance. So usually the refractive index is an increasing function of frequency, and that means that this equation is incompatible with this equation. So what do you do? So there are a few possibilities. By far, I'd say the most standard is to make use of what's called birefringence phase matching. You find a birefringent material. Well, you can have uniaxial and biaxial. Uniaxial is simpler, so let's assume a uniaxial birefringent material. A uniaxial material is characterized by two different values of the refractive index, one called the ordinary value, the other called the extraordinary value of the refractive index. Here's a picture that attempts to define what we mean by ordinary and extraordinary. In a uniaxial crystal, there is one, that's what the uni means, there is one special direction in the crystal. This is called the optic axis, and it's conventionally designated as the C-axis of the crystal. So let's orient the diagram so that the optic axis and the k-vector of the incident light are in the plane of the diagram here. And let's define the angle theta to be the angle between the k-vector and the c-axis. Now, light that is polarized perpendicular to the plane of the diagram is known as the ordinary polarization. Light polarized in the plane of the diagram is called the extraordinary polarization. And I think you can almost see why this is ordinary. As you change the angle theta, the electric field, in this case, is always perpendicular to C. On the other hand, for the extraordinary polarization, as you change the angle theta, the projection of the polarization onto the C-axis changes. And since the whole nature of the refractive index is the magnitude of the oscillating dipole that you set up, and since we're thinking of a material that is anisotropic, you'd expect something extraordinary to happen here, but not happen here. Now, this was worked out a very long time ago, 1965, by Midwinter and Warner, and they introduced a classification scheme that is universally used. They consider two different cases. You can imagine a positive uniaxial crystal, meaning that the extraordinary refractive index is greater than the ordinary, or you can imagine a negative uniaxial crystal in which the extraordinary refractive index is smaller than the ordinary refractive index. Let's consider this case here because that's the way I drew the picture. Now, they say there's two types of phase matching, which we can call type 1 and type 2. Type 1 means that the two low-frequency waves have the same polarization. Type 2 means that the two low-frequency waves have orthogonal polarizations. And in either case, when the whole trick is that you use birefringence to compensate for the dispersion. So let's see how that would work. Okay, here the ordinary is always bigger than the extraordinary. So if you take your low frequency waves and polarize them as ordinary waves, and take your some frequency wave and polarize it as extraordinary, then the birefringence, this effect, will tend to compensate for the dispersion, this effect. And that's what's said right here, that you want the high frequency wave to be extraordinary, you want the low frequency wave to be ordinary. And okay, so this is one standard way of producing phase matching, and you can work out all the details if you want. You can, for simple cases, you can do it with pencil and paper. More complex cases, especially for biaxial crystals, you just need to do it numerically on a computer. But I think no matter how complicated the situation is, you want to have some intuition. And I think these pictures here display the intuition. Now, there's another way of achieving phase matching, and this is called quasi-phase matching. And this is what Marty Fayer is going to be telling us about in a day or so. Let's see, quasi-phase matching, well, in Armstrong, Bloomberg, and Duquois, and Pershan, in their very first paper, they talk about this. And people say, well, this is so impractical, no one will ever make it work. Marty made it work. So the embarrassment in Marty's presence for me to explain how this works. So let's contrast two different situations. You can imagine a single domain crystal. Here the C-axis is pointing in the same direction everywhere. You can have a periodically poled crystal, and here the C-axis is periodically forced to change directions. And let's define lambda to be the period by which we invert the polarization of the material. By the way, these are called domains. This is just convention. You could say that this is a single crystal and this is a stack of different crystals, of different crystal orientation. But it's such a subtle change. The direction of the polarization depends on very subtle changes of the positions of the atom within the unit cell that people use the word domain, just as in magnetism. Right? We talk about magnetic domains. Here we talk about crystalline domains. Okay, so using a very tricky method that I'm sure Marty will tell you about, one is able to create a crystal in which the C-axis is periodically inverted. Why is this a good thing to do? So let's contrast several situations here. Here we'll plot the field amplitude on this axis as a function of propagation distance inside the material. Okay, so if you have a wave vector mismatch, you find that you do not get any coherent buildup of radiation. You just get this periodic oscillation of field amplitude. Light first flows from the fundamental into the second harmonic, then it flows back from the second harmonic into the fundamental over and over again. You get no net pickup of intensity. Now, what about perfect phase matching? Well, we talked about that already too, and we found that the field amplitude increases linearly with propagation distance, and we said that the intensity increases quadratically. Now, how does quasi-phase matching work? Well, just at this point here, where the field, where the generated field was going to flow in the opposite direction, you flip the sign of chi2. And then instead of going down, it goes up. And just at this point here, where it was going to come down, you flip the sign of chi2, and it continues to go up again and again and again. So you ask yourself, which would you rather have, this, or this? clearly you would rather have this. But if your only option is to have this or to have this, you would much rather have this, because here you do have a coherent monotonic buildup of the overall intensity. And Marty will tell us a lot more about this. Okay, nonlinear optics with focused laser beams. Now, everything up until now has made a very common but very crude approximation. We assumed that the laser beams were infinite plane waves. Of course, I don't have enough money to buy a laser that produces infinite plane waves because they carry an infinite amount of power. So this is just an approximation. Real experiments don't use infinite plane waves. The light that comes out of most lasers is a Gaussian laser beam. Beam waist looks like this. So then the question is, what is the best way to maximize the efficiency of the harmonic generation process, given that you do have a laser beam, a Gaussian laser beam, let's say. So one thing you could do is just not focus the beam at all. But a moment's thought tells you that that's probably not the best thing to do, because if you focus the beam a little bit, you can increase the intensity, increase the field strength, you get higher efficiency. But you don't want to overdo things either. If you focus it very tightly, you find yourself in a situation in which you have very high intensity here, but very weak intensity here, and very weak intensity here. So effectively, you're using only a very, very small fraction of the length of the crystal. And since the efficiency scale is like the square of the length of the crystal, clearly this is not very efficient either. So you might then convince yourself that the best thing to do is focus the laser beam something like this, so that the Rayleigh range of the laser beam is approximately equal to the length of the crystal. And many, many years ago, 1968, a different Boyd, certainly not me, I was a very young man then. People sometimes confuse me for the other Boyd, and then say, and by the way, since you must be at least 95 years old, you sure look good. Okay, so different Boyd went through this in detail, and they said that, well, here I said you'd want them to be about the same. They actually want the confocal parameter, half the Rayleigh range, to be equal to L over 2.84. This comes out of numerical evaluation of an integral. And remarkably, you don't want delta k equal to 0. You want delta k to be non-zero. So how do you understand that? Well, remember there's the gooey phase shift. So any beam of light suffers a pi radian phase shift as it passes through the focus. In linear optics, this is a curiosity that you have to work very hard even to observe. In nonlinear optics, it's very important, because if the fundamental beam experiences a pi radian phase shift, then the square of that field amplitude suffers a 2 pi radian phase shift. And it cannot efficiently couple to the second harmonic beam, because the second harmonic is also a Gaussian beam, which suffers a pi radian phase shift. So you have to externally introduce a phase shift into the process to overcome the gooey phase shift. Oh, and when you take this into account, you have this very complicated expression quoted in this paper. And remarkably, under conditions of optimum focusing, you no longer have an L squared scaling dependence. It's only linear with L. It was L squared if you had an infinite plane wave. Once you focus it properly, you get much more out, but you only get a linear scaling. Oh, and this is to tell you that optical waves are not the only waves that I study. In fact, this was taken just 3 weeks ago, maybe 4 weeks ago now. I was I was invited to a conference in Tokyo, and I convinced the organizers that a man my age can certainly not make that long a trip without stopping over halfway to recover from the jet lag. So, so I stopped halfway, but I stopped in Hawaii and spent a few days on the beach. Okay, so mechanisms of nonlinearity. Let's start in with this, and I do plan to stop a little bit early for questions. Okay, mechanisms of optical nonlinearity. Let's call this a trend diagram here. Here are a variety. This is still visible, yes? To change batteries in the green laser pointer. Okay, so here are a list of some physical mechanisms that can produce an optical nonlinear response. Here's a typical value of N2 for this mechanism. Here's a typical value of chi3 for each of these mechanisms. And here's the response time. And what I mean by response time is, let's say you turn on a laser beam and you ask, how long does it take for the nonlinear response to reach its steady state value? Oops. How long does it take to reach its steady state value? So the electronic polarization, this is what we've been talking about until now. You take the electron cloud, you pull it to one side of the nucleus. On the next half of the oscillation of the laser field, you pull it the other way. So the response time here is of the order of the Bohr period. Go back to your Bohr model of the atom and ask how long does it take the electron to circulate around the nucleus. So people with a bit of excess call this instantaneous response because except for people like Paul Corkum, who can measure femtoseconds. Usually in photonics, we don't think we can measure things that are that short. So from many practical points of view, we can call this an instantaneous response. Now, if you look at this chart, you see that this is an example of what's called there is no free lunch. You can get a nonlinearity that is very, very large, but only at the expense of having a nonlinearity that is very slow. And in fact, this almost makes sense. If this is an instantaneous nonlinearity, these are integrating nonlinearities. Thermal response being an obvious example. You turn on a laser beam, the sample starts to heat up. After a second or a millisecond, it will reach a steady state temperature. Because it's at a new temperature, it has a different refractive index. This is not deep, but it tends to be a very strong nonlinearity. And it's an integrating nonlinearity. So as you go up and down this chart, okay, and we don't have time to go through everything, molecular orientation, electrorestriction, saturation effects. But it's the trend that I really wanted to call to your attention here. Okay, now, if you really wanted to, you can actually calculate the value of chi2 associated with the electronic response, right? We have Schrodinger's equation. We really think that we know how to calculate these things. Bloomberg did this first. I've just rewritten this in my own notation here. So you can calculate a quantum mechanical expression for the magnitude of the second order nonlinear response. We have 1, 2, 3, 4, 5, 6. We have 8 terms here. For each of these terms, we can write down a Feynman diagram that explains the origin of this term. Is this important or isn't it? First of all, almost never does one, rarely does one have enough knowledge of the actual structure of a crystal that you would know all of these parameters. So it is very little predictive value. On the other hand, it's nice to know that it can be done. It's nice to know that the laws of quantum mechanics do lead to explicit predictions for the size of nonlinear optical effects. And also it gives you the proper scaling laws that chi2 depends on the product of 3 dipole matrix elements and on 2 resonances, a single photon resonance and a 2 photon resonance. Here omega p and omega q are the 2 input fields. So this tells you that if omega p is close to a resonance of the material, you'll get a large response. It tells you that if omega p plus omega q is close to a resonance, a different resonance, presumably, of a material system, you will also get a very large nonlinear optical response. Okay, so you can use quantum mechanics. You can go to exactly the opposite limit and try to develop simple intuitive tools for understanding the nature of the nonlinear optical response. Well, here we've talked about this already. You can ask yourself, what is the actual potential well that binds the electron to its equilibrium position? And if you like the Lorentz model of the atom, you say, well, not all springs are Hooke's law springs. This is a non-Hooke's law spring. How do you estimate the size of this? Well, let's think now of a centrosymmetric material. So chi3 would be the lowest order nonlinear response. We want to guess or estimate the size of chi3. Here is the argument that this term will be comparable to this term. The correction term is of the order of the dominant term when the electric field that you apply is comparable to the electric field that holds the atom together. So this would be the charge, I wrote this in Gaussian units, charge of the electron divided by the square of the Bohr radius. So if you, that tells you that chi3 would be of the order of chi1 divided by the square of this atomic field strength. Chi1, at least for condensed matter, is of the order of unity. So this is just the 1 over the field strength squared. Again, in Gaussian units, this is 10 to the minus 16 ESU, which is embarrassingly close to what people measure in the laboratory. Raising the question, why would you ever do this when you can make an argument of this level of simplicity and it gets you in the right ballpark? Okay, so that's how you estimate the size of chi3. Of course, this generalizes. You can estimate chi2 by the same argument. And let's just, in the time before the break, let's just take a look at some of the other mechanisms for optical nonlinearity. There's the molecular orientation effect. I'm thinking of this in terms of liquids. Paul Corkum is going to tell you, I suspect, that he is he's studying these effects in gases and just looks at how molecules are going to orient themselves in the electric field of his laser beam. But for the case of liquids, as maybe you know and maybe you don't know, in which case I'll finally have taught you something, carbon disulfide has a very large optical nonlinearity, chi3 nonlinearity, and you can buy it anywhere. It smells bad, but you can buy it anywhere. So people often use it as a calibration standard. I mean, it's always difficult to make absolute measurements. So very common, you say, I found a new material. I will measure its nonlinear response and compare it to that of carbon disulfide. So carbon disulfide is it's a cigar-shaped molecule. The nature of the nonlinearity, here's a crude approximation to a cigar-shaped molecule. The nature of the nonlinearity is that if you apply a laser field E, this molecule is going to experience a torque, and this torque is going to tend to align the molecule with the electric field of the laser. Now, of course, since the molecule itself is anisotropic, if you present the larger polarizability to the direction of the electric field, the refractive index is going to go up. So let's just work out a few of the details here. You can think of this two ways. You can think of this as the shape of the molecule, or you can think of this as the ellipsoid that represents the tensor that describes the polarizability of the molecule. In the second case, the long axis here, we'll call it alpha perpendicular, parallel rather. This is the polarizability parallel to the symmetry axis. Alpha perpendicular is perpendicular to the symmetry axis. As drawn, alpha parallel is greater than alpha perpendicular. Now, the induced dipole moment is alpha dot E. So even though we've applied the electric field in this direction, the induced dipole moment is going to be in this direction. It's going to be offset a little bit to the right because this component of the polarizability is bigger than this component of the polarizability. Now, the molecule experiences a torque, and the torque is the dipole moment crossed into E, and that torque will be oriented so as to take the molecule and twist it so that it points in that direction. So you go through that argument. You find that the linear susceptibility is the number density of molecules in the sample times the weighted average of alpha parallel and alpha perpendicular. Of course, there are two directions in the perpendicular direction. More interesting for the current purposes, you can calculate chi3, and you find that it's given by this expression here, a numerical factor times the square of the difference of the polarizability divided by kT, K being Boltzmann's constant here. So how do we understand that? Well, in a liquid, there's fluctuations associated with Brownian motion. These fluctuations will tend to randomize the orientation of each molecule, but you have this applied laser field that's trying to align them along the direction of polarization. So it's a trade-off of these effects. And again, it's always positive, even if alpha perpendicular is larger than alpha parallel, because then you're always twisting the molecule to present the larger value of the polarizability in the direction of the applied electric field. And, I'm not sure where this fits in logically with the talk, but it's too important not to fit it in. I call this the two great ironies of nonlinear optics. The first irony is that silica has about the smallest value of chi3 of any known material, yet it is extremely nonlinear in the sense that if you study fiber nonlinear optics, you find enormously strong effects, which we will hear about this evening by Professor Millette. I don't know how to say it. That's why my friends failed me dramatically. Okay, so in tonight's lecture, we're going to hear about fiber nonlinear optics. I guess the point is that even though chi3 is very small, the absorption per unit length is extremely small. Light can propagate for many kilometers in an optical fiber. So it's the cumulative effect of propagating over very long distances that can build up in optical fibers. Okay, the second great irony is that silver and gold have very large values of chi3, but they are nearly opaque. So it could make you cry, right? You spend a large fraction of your life trying to find materials with a very large value of chi3. You finally find one. Hey, sir, I have good news and bad news. This has a huge Chi3. Well, it doesn't transmit light, but that's that's an issue of detail. But more seriously, then recognizing this fact, people try to do something about it. One is to have a dilute colloidal solution of silver or gold nanoparticles. So, I mean, that doesn't really solve the problem. You're just making it more dilute. You can try to make use of the plasmon resonance. So you make the effective Chi3 even larger by hitting the plasmon resonance of the material. Or you can try to find tricks to make the light, trick the light into tunneling inside the material. And we'll talk about that later if there's time. And perfect. I wanted to leave time for questions, but I wanted to end at a logical stopping point. So starting a new topic seems like a logical point to stop. So, Pascal, the official part of the lecture is over, and I'm going to just open this up for questions. So we're open, and thank you very much.